Hello everyone. Today we will talk about the exponential distribution and other continuous distribution. The exponential distribution is a continuous distribution that is sometimes used to model the time that elapses before an event occurs. Such a time is often called a waiting time. For example, the random variable could be the time I will wait until a next customer showed up, or the time we will wait until an atom emit, or the time for a product to come. And usually if x has exponential distribution, then the notation is exponential, and the only parameter you need is lambda, where lambda is the rate of occurrence of the event. The probability density function is f of x, which is lambda e minus lambda x. If I plot these, it will be this graph for different lambda. So for larger lambda, that is a high rate of occurrence, x, the waiting time will be short. So most of the waiting time will be, in this case, between 0 and 0.5 for lambda 4. Versus for lambda 1, then the waiting time will be longer, 1.5. And if x is a waiting time, then it has to be larger than 0. And if we want to find the cumulative distribution function f of x, we just integrate f of x dx from 0 to any value of x. That will give us f of x, which is the same as the probability that the random variable x is less than this value. If I need to find the average or the mean of the exponential random variable mu x, the average waiting time, it will be 1 over lambda. So if the rate of occurrence is 4 per minute, then the average waiting time y of x will be 1 over lambda, so that is 1 over 4, that is 0.25 minutes. If I want to find the mean, I can carry out this integration. So mu x equal the integral from the lowest value the random variable x can have to the largest value, which is infinity, of x time f of x, probability density function. And that will be from 0 to infinity x lambda e minus lambda x dx. And if you carry out this integral, you will find it to be 1 lambda. And the same thing, we can find the variance of x to be from 0 to infinity x squared f of x minus mu x squared. And mu x here, we just found that this one. And if you carry out this integral, that will be the variance of the exponential random variable, 1 over lambda squared. Now we can link the exponential distribution to the Poisson process. So if I have a Poisson process, then it will have a rate, which is lambda. It's the rate of occurrence. Now, if I am not interested, what's the probability x equal 5? That means the event will happen 5 times in 1 minute. But all I am caring is about the time between the events, t. Then that will be the exponential. So the process is Poisson. It's a process that happened that many times over a specific interval, over a specific space. But what I am interested is not on the probability that 5 times it will happen in 1 minute or 2 minutes, but I am interested in what is the probability I will be waiting 10 minutes or 5 minutes between events occurrence. Then in this case, t will be exponential. And lambda here is the rate of occurrence for the Poisson process. Let's take this example. A radioactive mass emitted particle according to a Poisson process at a mean rate of 15 particles per minute. So lambda is 15 particles per minute. Okay? At some point, a clock is started. Now the question is, what's the probability that more than 5 seconds will elapse before the next emission? Since the unit is 5 seconds, we have to find really lambda in terms of second, the rate in terms of second, not in terms of minute. So that means my new lambda here will be the old lambda dividing, so let's call this odd lambda, the odd lambda divided by 60 to find the rate per second. So that is 15 divided by 60. So that is 1/4 particles per second. Now to find the probability, and let's call the random variable t, the waiting time until next emission, larger than 5, is the same as the probability 1 minus probability t less than 5. And then 1 minus, that probability is just the cumulative distribution function with the random 5. And in the previous slide, we found these to be 1 minus e minus lambda, the random variable x. In this case, it's t. So this is e minus lambda t. And that is e minus lambda is 1/4 and t is 5. So that's e minus 5/4. And this should come 0.2865. Now, you could find this probability by carrying out the following integral. The integral from 5 to infinity of f of x dx. And it's an easy integral. And the probability density function is lambda e minus lambda t dt. And if you carry this integral, you should get the same answer. Now, what is the mean waiting time until the next particle is emitted? Now we want to know what's the mean waiting time, and that will be mu of t, and we found it 1/lambda, and that will be 1/1/4, so that is 4 seconds. Or you could have used that rate, lambda 15, 1/15, and that will be minutes. Okay, let's look at this example. The distance between flaws on a long cable is exponentially distributed with a mean 12 meters. So we have a long cable, and there could be a flaws here, another flaws here or here. The distance between flaws, and let's call it a random variable x. They gave you the mean of the random variable x, which is mu x equal 12 meter, and x is exponentially distributed with that mean. So if x is exponential distribution, we need lambda. So in this case, we know that mu x is 1/lambda. So I can solve this one. Lambda equal 1/mu x. So that is 1/12 flaws per meter. That is the rate of flaws. Now the question here, find the probability that the distance between two flaws is greater than 15 meter. So they want what is the probability that x is greater than 15. So this is the same as 1 minus the probability x less than 15. So this is 1 minus, use the cumulative distribution function, 1 minus e minus lambda x. So that is just e minus lambda x. And that will be e minus lambda, we found it 1/12, and x, we want the probability larger than 15. So that is 15. So that is e minus 5/4. And if you use your calculator, you should get 0.2865. Find the probability that the distance between two flaws is between 8 and 20. So the probability x is larger than 8 and less than 20 will be 8 to 20 times the density function, which is lambda e minus lambda x dx. And if you carry out this integral, it will be lambda divided by minus lambda e minus lambda x evaluated from 8 to 20. So this will be minus e minus lambda 20 minus e minus lambda 8. And this is just e minus lambda is 1/12. So that's e minus 8/12 minus e minus 20/12. If we use our calculator, we should get, so there is 32.45% chance that the distance between flaws is between 8 and 20 meters. If we want to find the median, then we have to carry out this probability. from 0 to x, let's call the median m of the density function e minus lambda t dt, and if this is the median, then the area under this should be half, and when you carry out this integration you should get 1 minus e minus lambda xm equal 0.5, and here it will be e minus lambda xm equal half. Take the natural log, you will get here minus lambda xm equal the natural log of half. Then you solve for the median xm. So the median is 8.318 meter. It's a little bit less than the mean, because remember the exponential, you can think of it as a skewed to the right. So if the mean is 12 meter here, then the median will be 8.318. So half the area here, the area from 8.318 to infinity is half. And the mean is larger than the median because it's skewed to the right, so those large values pull the mean toward the right. Last part is find the standard deviation of the distance. And the standard deviation of the distance for exponential, we found it, the variance t. I started here calling it random variable x, now I'm calling it t, it's the same. So the variance is 1 over lambda square. So that is 1 over lambda is 1 over 12 square. So then from here, the standard deviation will be just 12 meter. Okay, one important property of the exponential distribution is lack of memory. And what does that mean is the following. Imagine there is an operator that picks up phones, and someone here is waiting for the operator to answer the call, and he has been waiting 5 minutes, and someone just made the call now. The waiting time for this person A or this person B that just called now will be equally likely. So that means this operator or this operator, when one of them is free, it may by chance pick up this call that has been waiting for 5 minutes, or it may pick up this phone call that just make the call. So there is no memory. Just because you waited 5 minutes, the probability that they will answer your call or your waiting time will be less. And mathematically, we say the probability that the waiting time larger than t plus 5, t here could be 10 seconds, wait s is 5, given that I already waited 5 minutes, is the same thing as the probability that I will be waiting 10 minutes. So this guy here already waited 5 minutes and want to know what's the probability his total waiting time will end up 15. Already waited 5, now what's the probability you will wait another 10, so that's 15. It's the same as the probability that t is larger than 10. Just because you already waited 5 minutes, that doesn't mean the probability t will be less than 10. And to prove that, we use the conditional probability to prove this one. The conditional probability will be probability t larger than t plus s and t larger than s given by the conditional probability t larger than s. So I converted this conditional probability to this one. Just I use like probability A given B is the same as probability A and B divided by the probability of B. So I use this conditional probability. Now, if I assume this is 10 minutes and this 5 minutes and this is 5 minutes, that and intersection, if he already waited 15 minutes, then definitely already waited 5 minutes. So this is just same as the probability t larger than t plus s divided by probability t larger than s. And if I use a cumulative distribution function, this is just e minus lambda t plus s divided by e minus lambda s. And if I bring this in the numerator, this will be e minus lambda t minus lambda s times e plus lambda s, and this is just e minus lambda t. And that is exactly the same as this one. If I tell you what's the probability t larger than t, that is just e minus lambda t, say. And that's what we mean by lack of memory. Just because you waited 5 minutes doesn't mean the probability of waiting another 10 minutes would be any different from a person who just came and asking what's the probability I will be waiting 10 minutes. It will be the same probability. So if we look at this example, the lifetime of a particle integrated circuit has an exponential distribution with a mean 2 years. Find the probability that the circuit lasts longer than 3 years. So here we want to find the probability t is larger than 3 years. So that will be e minus lambda 3. Assume the circuit now 4 years old and it's still functioning. Find the probability that it functions for more than 3 additional years. That will be the same thing. Probability t 3, and it has been already working for 4 years, given that s 4 years. That is the same as the probability t larger than 3. And that will be the same probability, and you should get the same answer. Now, we said if x is the random variable that has exponential distribution, then the only parameter we need is lambda. And now I want to estimate this parameter, lambda, which is the rate of occurrence. Well, one way to estimate it is to run the experiment several times and they keep track of the waiting time. X1, another time I conduct the experiment or monitor the emission time for an atom, X2 and X3. So I collect all these times and then I find the average of the waiting time, which is x1 plus x2 plus x3 plus x4 divided by n. If I run the experiment 4 times, n will be 4. And that will give me the average waiting time. Then the estimate of the rate will be 1 over the average waiting time. And this is the estimate. The uncertainty in the estimate will be lambda, the estimate, divided by square root of n, just like the same as the discrete distribution. The more data I take, that means the larger n, the smaller the uncertainty in my estimate of the rate of occurrence, lambda. In this section, we will go through the uniform distribution, the gamma distribution, and the Weibull distribution. A uniform distribution has 2 parameters, a and b, and a is the smallest value the random variable x can have, and b is the largest value the random variable x can have. And if it's uniform, so if I plot x here, this is the random variable, and this is the range where x can be, from a to b. Then if I plot f of x, the probability density function, if it's a uniform, then that means this will be constant. So the probability x will have this value, or this value, or this value, or this value will be the same. And if this is a probability density function, then this a has to equal a certain value such that if I take the area here, it has to be 1. So then the height, which is capital A, times the width, which is b minus a, must equal 1. So then this is a will equal 1 over b minus a. And that's the probability density function for the random variable x, which is this. And the random variable x will be between a and b. And if I need to find the variance and the mean of the random variable x, this is the mean, mu x, and we can find it very simple by carrying out this integral. Mu x equal x f of x for all possible value of x from a to b. And this will be a to b x, and the density function is 1 over b minus a dx, so that is 1 over b minus a, and the integral of x is just x squared over 2 evaluated from a to b. So this is 1 over b minus a, and then this will be b squared minus a squared over 2. And I can express this as 1 over 2 b minus a, and this will be b plus a times b minus a. And this cancel and they end up with b plus a over 2. And that's the mean. And the same thing we can carry out the integral for the variance, which will be the mean of x squared minus mu x squared. So that will be the integral from a to b x squared f of x, which is this one, minus a plus b over 2 squared. And if you carry out if you carry out this integral, that will be the variance. And you even can find the mean here easily from the graph here. If I told you that this is the two possible extreme value for x, this is the lowest, this is the highest, what's the mean? It will be in the middle. So that will be b plus a divided by 2. If that was 5 and this is 10, then it will be 15 a plus b divided by 2, that's 7.5. So the mean will be somewhere here, 7.5. Okay, let's see an application for a uniform distribution. When a motorist stops at a red light at a certain intersection, so we have this intersection here, and there is a red light here, and a small car here. The waiting time for the light to turn green in seconds is uniformly distributed on the interval 0 to 30 seconds. And we should expect that. That means there is a chance when I come to the intersection, the light is green. So the waiting will be 0. I won't wait. And there is a chance that I'm out of luck. About time I came to the intersection, it turned red. Then I have to wait the whole 30 seconds until it turned green again. And the probability that I was 0 or 10 seconds or 20 seconds or 30 seconds is the same. So it looks like a uniform distribution. Now find the probability that the waiting time is between 10 and 15 seconds. So that means if I call the waiting time is x, so they want the probability that x is larger than 10 and less than 15. Well, I have to find a. Well, a, the area, the height here, times the width here, which is 30, has to equal 1. So the height a will be 1 over 30. Or just use f of x is 1 over b minus a. And that should give you 1 over 30. Okay, then this probability will be integral from 10 to 15. The probability density function is 1 over 30 dx. So that will be 1 over 30x evaluated from 10 to 15. So that's 1 over 30, 15 minus 10. So that's 5 over 30. And this should give us 0.167. So that's 16.7% chance that I will be waiting between 10 and 15 seconds in the intersection. The next distribution is the gamma random variable. And the relationship between the gamma and the exponential distribution is the following. So when you have many random variables that have exponential distribution, x1 plus x2 plus xr, that means I am interested in the waiting time for the third event to happen if r equals 3. Or I am interested in waiting for the rth event to happen. What is the waiting period? That's what I'm interested in. See, the exponential is the waiting interval for the first event to happen. Then it's exponential. But the gamma, I am interested on the waiting time for the rth event to happen. Then I am adding the time it takes for the first event to happen, the second event to happen, until the rth event to happen. If r equals 3, that means I will calculate the time until the first event to happen, the time for the second event, the time for the third event to happen. And if the total time, I call it x, then x will have a gamma distribution with two parameters. R is the number of events that I'm interested in, and lambda is the rate of occurrence for the events. Then that's a gamma distribution. And if I look into the probability density function for the gamma distribution, it's this one. And if I plot these for different value of number of events and the rate of events lambda 1 or r3 lambda 2 or r5 lambda 1, these are the plot I would get. When I'm interested in the waiting time for the first event to happen, then it's just the exponential, which is this. The more event I took into consideration, the waiting time for 5 event x1, x2, all the way to x5, like this case, then it's become more and more, it looks like a Gaussian distribution. So if R is 20, this will look almost like a Gaussian distribution. And the gamma function here, it's very complex. But if R is an integer, then it's very simple. Let's look at this slide, then we will come back to this slide. The gamma distribution, the function. This is the function. So here R could be integer like 1, 2, 3, 4, or R could be real like 1.1 decimal, 1.2, 1.7, and so forth. Or R can be complex number like 3 plus J4 or A plus JB, where A can be any value and B can be any value. Then the gamma function here for R is this integral, which is a complex integral. We will not deal with it for this course. But for simple case, if I am interested in events, then R will be an integer. 2 event, 3 event, 4 event, 5 event, 7 event. Then gamma R is very simple. It's just this one. R minus 1 factorial. And gamma half is just the square root of pi. So that's what's the gamma function. All right, let's go back here. If x has a gamma distribution, then the mean of x will be r over lambda, which makes sense because for exponential, r is 1, and the mean we find it 1 over lambda. So now if x has 3 waiting period or 5 waiting period, then the mean of x, the mean of the waiting time for r events, it will be 1 over lambda time r, which is this, r over lambda. And the variance of x will be 1 over lambda square, which is the variance of exponential. But now there are r events, not just one. So it will be r over lambda square. Let's take this example. Assume that arrival times at a drive-through window follow a Poisson process with mean lambda equal 0.2 arrival per minute. Let t be the waiting time until the third arrival. So now r equal 3 and x is gamma distribution with r3 and lambda 0.2. Find the mean and the standard deviation. Well, the mean of x is just r over lambda. So the mean of the waiting time for the third arrival is 3 over 0.2. So that's 15 minutes. So in average, I will be waiting 15 minutes for a third customer to show up. The standard deviation of x is the square root of the variance, which is r over lambda square. So that's the square root of 3 divided by 0.2 square. And if you calculate these, it should be 8.66 minutes. Find the probability that the waiting time will be equal or less than 20 minutes for 3 customers to arrive. So to solve this problem, it will be from 0 waiting time to 20 minutes of the f of x dx, the density function. So this will be from 0 to 20, and the density function is lambda r xr minus 1 e minus lambda x over gamma r dx. So this is from 0 to 20. Lambda to the power of r, lambda is 0.2, r is 3, x, r minus 1, so that's 3 minus 1, that will be 2, e minus 0.2 x divided by gamma 3 dx. I will take this constant out, so that will be 0.2 to the power of 3 divide gamma 3. Gamma 3 is 3 minus 1 factorial. So that's 2 factorial. So that's 2 factorial. That is 2. So I have here 2. The integral from 0 to 20 x squared e minus 0.2x dx. And now you can use following integral to integrate this quantity, where a here is the minus 0.2. So this will be 0.2 to the power of 3 divided by 2. And if you plug numbers, you should get 0.762. And this is the probability I will be waiting that long, 20 minutes or less. it's 76.2%. And we should expect that because we just found the mean waiting time is 15 minutes. So the probability that I will wait longer time is going to be very high for 3 events to happen. Now, in Weibull distribution, you can read it in the textbook, but it's a very important distribution because it models the lifetimes of a component. So now X, the random variable, is how long these component transistors or memory or light bulb will last 1,000 hours or 3 years or 4 years. I want to find that probability. Then we use the Weibull distribution, and there is 2 parameters, alpha and beta. And if I show the probability density function, it's this one for the random variable X with 2 parameters, alpha and beta. And if I plot this function for different value of X that depend on different alpha and beta, I will get this curve. And they found this function model accurately the lifetime of component. And we are not going to go through the detail, but the mean of this random variable that has Weibull distribution and the variance is the following. It's very easy. Now software can calculate this very simple because this may not be an integer. So the gamma function will be a complex integral. And this example, we are not going to go through the detail, but the lifetime of a cooling fan in hours that is used in a computer system has a Weibull distribution with alpha 1.5 and beta 0.001. What's the probability that fan lasts more than 10,000 hours? So that will be the probability X larger than 10,000 hours. So this is the same as 1 minus the probability X less than 10,000 hours. And if you calculate this, that will be the probability 0 to 10,000 of this density function. Alpha, which is 1.5, beta, which is 0.0001 to the power of alpha, which is 1.5, X 1.5 minus 1, that is 0.5, E minus beta 0.001, X to the power of alpha, which is 1.5 dx. And you can use a computer to calculate this integral or approximate it and find that probability. I will stop here, and the next video will be about point estimation of a random variable parameter. Thank you.